Good evening, ladies and gentlemen. Welcome to another edition of NAMSSN tutorial. So this is a complex analysis one, and then the topic we are looking about this evening is complex numbers. So let's start with coordinate geometry. Suppose I'm having point A to be 3,1, for example. So the meaning of this 3,1 is x is 3, y is 1. And if I have point B to be, let's say, -5, -3, it means x is -5, y is 3. There is another way of representing these coordinates. So we call it rectangular form. So if I express this 3,1 in form of 3 plus I, so meaning that x is 3, y is 1, whereby this 3 that I put here, so we call it the real part. And this I that is here is the imaginary part. So if I have -5 comma -3, it's just like having -5 -3i. So -5 -3i. So this -5 is the real part, this -3 is the imaginary part. And then so we can now define complex number as any algebraic expression in form of, so a complex number is any number in form of a plus ib or a minus ib, where a represents the x coordinate, that is the real part, and b represents the imaginary part. So all these complex numbers, we can actually represent them on xy plane. So we can represent complex number on xy plane. So let me take this 3 plus I, for example. 3 plus I. So this is a y-axis and this is a x-axis. 3, it means that x is equals to 3. Suppose I'm putting x equals to 3 here. X equals to 3. I is like 1i. So it means y equals to 1. Let's say y equals to 1 is here. So if I join them together, they will meet at this point. So I will just rule a line from origin like this. So this line represents this complex number 3 plus I. And the other one that is here, -5 -3i, meaning that x is -5, y is -3. So if x is -5 is around this corner and y equals to -3 is around here. So if I join them together, so let me clean this dotted line. So this is like -5 -3i. -5 -3i. So this is a way of representing complex number on xy plane. So this diagram that I draw now is what is called Argand diagram. So this is what I call Argand diagram. So Argand diagram is a way of representing complex number on xy plane, like plotting them on graph. So Argand diagram, it is the way of representing complex number on x and y plane. Now, you must have been wondering about this I that I'm using. I. So what is that I? So let's briefly talk about that I. So that I is known as a iota. So the symbol of that I is iota. So let's talk about the iota I. So this I, where does it come from? Suppose I'm having a quadratic equation like x squared minus x minus 1 equals to 0. I want to solve this quadratic equation. And then I prefer to use a quadratic formula, x equals to -b So here my A is 1, B is -1, C is -1. So if I use quadratic formula to solve this, that's a minus B minus -1, that's +1, plus or minus square root of B squared minus 1 whole square is 1, minus 4AC. Okay, let me turn this one to 1, turn it to 1. Okay, so minus B, that's -1 plus or minus square root of B squared. 1 square is 1, minus 4AC, that's 4 times 1 times 1, all over 2A, all over 2A, that's 2 times 1. You know, from here I'm going to have -1 plus or minus square root of, this is 4, 1 minus 4 is -3, all over 2. And if I press square root of -3 on my calculator, so calculator will give me math error or syntax error. But there is a way. So there is a way of going from here now. You know, from rule of third, if I have square root of AB, it's the same thing as having square root of A multiplied by square root of B. So if I have square root of -3, I can simply express this one as a -1 plus or minus -1 plus or minus square root of -1 times square root of 3, so that I will be able to isolate this minus that is causing problem here, all over 2. So I can just name this square root of -1. That is where this iota come from. So iota means the square root of -1. So if I now let this square root of -1 to be my I, so I will just have -1 plus or minus I root 3 all over 2. So what do I need there is this square root of -1. Suppose you are solving quadratic equation and you get something like square root of -16 here. You can just change this square root of -16 to -1 times 16, so that we can be able to separate this minus. So that -1, is the iota. So now we have now that we've established that I is equals to, now that we've established that I is equals to square root of -1, I is equals to square root of -1. If I take the square of both sides, so I'm going to have I squared equals to -1. So those are the basic things that we are going to be using during this course. So I squared is equals to square root of -1. So I squared is square root of -1. If they ask me what is I raised to power 4, so I raised to power 4 is just like having I squared with squared. And I squared is -1 all squared. -1 all squared. Minus times minus, that one is 1. So if they ask me to find what is I raised to power 11, for example. So I raised to power 11, I'll first say this is like I squared raised to power 5. This is I raised to power 10 now. So it will remain 1 I here now. So I squared, I know that I squared is -1 raised to power 5 times I. So -1 raised to power 5, odd power. -1 raised to power 5, -1, -1, -1, -1 times -1. So that one will be -1. So -1 times I, this one will give me minus I. So what if we have I raised to power 27, for example? I raised to power 27, that's like having I squared 2 times what will give me a number that is close to 27. 2 times 13. 2 times 13 is 26. Then with another I here. So I squared is -1 raised to power 13. 13 is odd number. So -1 raised to power odd number is -1 times I. That's minus I. So you can go over again and try what is I raised to power 50. So I raised to power 50 is I squared raised to power 25. I squared is -1. -1 raised to power odd is -1. Okay, so this is how this iota works. Now, so a complex number can be expressed in 3 different forms. So a complex number can be expressed in 3 different forms. So forms of complex number. forms of complex number. Number one is the Cartesian form. We have Cartesian form, Cartesian or rectangular form. That's like z is equals to x plus iy, real and imaginary parts. Number two is the polar form. So the polar form is z equals to r into bracket cos theta plus I sin theta. And we also have the exponential form. We also have the exponential form. The exponential form is z equals to r e raised to power I theta. So z equals to r e raised to power I theta. You observe that I've introduced another set of parameters, r and theta. So what is r and what is theta? So that r is what we call the modulus. R is the modulus or magnitude of a complex number, of a complex number. Let me say Cn. And what is r? How do we find r? Suppose I'm having a complex number z equals to x plus iy. You know the meaning of x plus iy is I will mark a point on x-axis and I will also mark another point on y-axis. So this is where, let's assume that this is where they meet. I'll draw a line like this. And if I do something to look like a right angle triangle from here now, so I will have this line is parallel to y-axis. So this one will be y. The line that is here is parallel to x-axis. And from our knowledge of Pythagoras theorem, this longest side is the hypotenuse, putting an angle 90 here now. This is the modulus. So that's r squared equals to opposite square plus adjacent square, x squared plus y squared. So the modulus of a vector, sorry, the modulus of a complex number is square root of x squared plus y squared. So this r is equals to square of the real part and the square of imaginary part. Then we take the square root of the whole thing. And what is theta? What is theta? Suppose I put an angle here now, angle theta. With our knowledge of sine, cosine, and tangent. From where if I said tan theta here is opposite over adjacent. The angle theta is here, is facing this side. So this side will be the opposite, and the one here will be the adjacent. So if I take the tan inverse of both sides, so tan inverse of y over x. So we need r. R is the modulus, and this theta is the argument. So theta is the argument or the direction. Theta is the argument or the direction. So I'll take few examples on this modulus and argument of complex number. Now, given that z is equals to, well, before I start solving problem on modulus and argument, in most cases, this theta, the angle theta here is always in radian. You need to be very careful here. So I will be using radian. And you remember we normally convert angle from degree to radian. Suppose I'm having an angle theta in degree. I want to change it to radian. It will now be that angle theta multiplied by pi divided by 180. If I have something like angle 60, for example, that's 60 times pi divided by 180. 60 here 1, 60 here 3. So it will be pi over 3. If I have an angle 120 and I want to change it to radian, because once you've gotten your theta here now, so that theta must be in radian if you want to compute what is here. So suppose I have an angle 120, for example, that's 120 times pi divided by 180. 0 cancels 0. 6 here 2, 6 here 3. That one will be 2 pi over 3. Okay? Now, let's say we have z. Z is equals to 1 plus I root 3, for example. Z equals to 1 plus I root 3 as a complex number. So I want to find the modulus. Find the modulus and argument of this complex number z. So z is equals to 1 plus I root 3. So how do we do it? So the modulus r, according to this formula, r is equals to square root of x squared. X is the real part. So 1 square plus y squared. Y is the imaginary part, root 3 all squared. So that's the square root of 1 square is 1, root 3 all square is 3. So 1 plus 3 is 4. So square root of 4 is 2. And what is theta? Theta is the argument. So theta is tan inverse of y over x. So theta is tan inverse of y. So y is always the imaginary part, root 3 all over x of this complex number over 1. So tan inverse of root 3, if your calculator is in degree, if you press tan inverse of root 3 over 1, you are going to have 60 degree. But you have to convert that 60 degree back to radian. So my theta will be pi over 3. So it is preferable to change your calculator to radian before you start solving any problem. So if you just press tan inverse of root 3, you have pi over 3. So this complex number now, the modulus is 2 and the argument is pi over 3. So the modulus is 2 and the argument is pi over 3. So if I want to express this complex number like this, the way it is initially is in this form, is in rectangular form. Z equals to 1 plus I root 3. So if I want to express it in polar form and in exponential form, so this particular complex number now, if I want to express it in polar form, so in polar form, we are going to have Z is equals to R. What is our R? 2 into bracket cos theta. Our theta is pi over 3. Cos pi over 3 plus I sine pi over 3. So that is the polar form of the complex number. In exponential form, Z is equals to R exponential I theta. So our R is 2 and our e raised to power I theta. Theta is pi over 3. E raised to power I pi over 3. So that is how we express this particular complex number in polar and exponential form. And before I solve problem further, so there is one thing about trig that I need to talk about, or is odd and even function. So because there will be some case whereby we are going to be having negative angle here, for example, negative angle. Okay, odd and even function. What is an odd function? Suppose you are having a function f of x. If a function f of x now, okay, let me put it in this form. So a function f of x is odd if f of minus s is minus f of x, and a function f of x is even if f of minus s is still equals to f of x. So you see the difference between odd and even function. So what do we want to use this thing to do in this context of complex number? Okay, suppose I'm having f of x now. Let's test. If f of x is x squared, I want to check whether this function is odd or even function. So if I take f of minus x, it's just like having minus s all squared like this. So minus s all squared, that's minus s times minus s, is x squared. So you observe that f of minus s is also equals to f of s. So therefore, x squared is an even function. Suppose I have f of x to be, let's say, 3x raised to power 5, for example. 3x raised to power 5. So f of minus x, that's 3 into minus x all raised to power 5. So minus times minus times minus times minus, in 5 places, you have minus. So this one will now give us minus 3x raised to power 5. So you observe that f of x, f of minus s is minus f of s, minus f of s. Our f of s is 3x5 and f of minus s is minus 3x all 5. So anything with power, anything with odd power is an odd function. So any algebraic function with an even power is an even function. So in trig now, let's say f of x is cos x, for example. And if I take f of minus x, that's cos minus x. So cos is an even function. So this minus, so it will not be affected. So we are still going to have cos x. So f of minus x is still cos x. So therefore, cos x is an even function, which tells us that suppose our angle here is minus pi over 3, for example. So by the time I put minus pi over 3 here now, cos minus pi over 3, that minus will not affect this cos. To still be equals to cos pi over 3 because cos x or cos theta or cos whatever is an even function. So cos is an even function. And then the other one, sin x, if f of x is equals to sin x, if I take f of minus x, that's sine minus x. So this minus, it will now move to the back of this sign. It will now turn to minus sine x, which means that sine x is what? Is an odd function. Sine x is an odd function. So here now, if my theta is minus pi over 3, for example, by the time I put sine minus pi over 3 here, so that minus will do what? It will now move to the back of this one. It will now turn to minus I sine pi over 3. Reason being that sine is an odd function. So for example, let's use another complex number. Let's say z equals to 1 minus I. If z is equals to 1 minus I want to express this one in, I want to find the modulus and argument and then express it in polar and exponential form. To find the modulus, this is the real part. This minus I is the imaginary part. So r is equals to square root of 1 squared plus minus 1 squared. 1 plus 1 is 2. So let me leave it in short form. So the modulus is root 2. And the argument, theta. So theta is tan inverse of, theta is where? Okay, theta is tan inverse of y over x, where y is the imaginary part. So tan inverse of minus 1, the coefficient of I is minus 1, all over 1. So tan inverse of minus 1 is minus 45 degree. Well, if I don't want to go, if I want to remain in the first quadrant, tan inverse of minus 1 is minus 45 degree. And what is 45 degree in radian? Go by this idea. If you have 45 degree, that's 45 times pi over 180. 45 here 1, 45 here 4. So this one will give us minus pi over 4 instead of having minus 45 degree. So if I now put it in polar and in exponential form. So in polar form, z is equals to r, this is our r, root 2 into bracket cos theta. My theta is what? Minus pi over 4 plus I sine theta. I sine what? Minus pi over 4. Minus pi over 4. Cos is an even function. So z equals to root 2 into cos pi over 4 plus I sine minus pi over 4. So because cos is an even function, so this one will be root 2 into, we are having pi over 4 will remain as cos pi over 4. Sine is an odd function, that minus will move to this side to now turn to minus I sine pi over 4. So that is how to express complex number in, okay, this is the polar form of it. If I want to express it in exponential form, z is equals to r exponential I theta. So that's r is root 2 e raised to power I theta. Our theta is minus pi over 4. Put that minus here. So e raised to power minus I pi over 4. Okay. So the next thing we are talking about is the logarithm form. Logarithm form of complex number. Now we know that complex number z equals to x plus iy. It can also be expressed as r into cos theta plus I sin theta, as we said earlier, and it can also be expressed as r exponential I theta. Now that is complex number z. Suppose I now want to find the logarithm of a complex number z, log z. If I start with this part, r exponential I theta, so it's the same thing as having log, if I change this z to the exponential form, I'm having log r e raised to power I theta, right? And you know from properties of logarithm, log a plus log b, if I have log a plus log b is equals to log ab. So here I have log r times e raised power I theta. So I can express it as log r plus log e raised to power I theta. And from here now, log r, what is r? R is the modulus. So I can change this r, you know our r is equals to square root of x squared plus y squared. So this r, we can express it as log square root of x squared plus y squared. And you know, whenever log and log is log and antilog, so they will cancel out. So we are going to have plus I theta. And what is theta? So theta is the argument from our previous explanation. Theta is the argument. So this one will be written as log square root of x squared plus y squared plus I tan inverse of y over x. So this is how we express log z in real and imaginary part. You observe that everything here will give us a certain number. So this is the real part. Everything here like this is the real part. And because of I that is here now, makes everything here to be the what? To be the imaginary part. So let's take for example. So if I want to express log 1 plus log 1 plus I root 3 in real and imaginary parts, log 1 plus I root 3. So based on the previous illustration, this 1 plus I root 3 is our z. It means that z equals to 1 plus I root 3. What do I need? I need the modulus. This r, I need the modulus. So from here, if I take r is equals to square root of 1 squared plus root 3 all squared. So root 3 all squared is 3. 1 plus 3 is 4. Square root of 4 is 2. And I also need theta. Theta is tan inverse of y over x. So this is why the imaginary part, theta here, tan inverse of y over x. So root 3 over 1. So tan inverse of root 3 over 1 is 60 degrees. And I'm not using degree, I will be using radian. So 60 degrees is pi over 3. So if I now express this log 1 plus 3i in this form, so log 1 plus I root 3 is equals to log of the modulus. This is my modulus. And here from our estimation, our modulus is 2. It will now equals to log 2 plus I tan inverse of y over x is our argument. Tan inverse of y over x is pi over 3 from here. So plus I pi over 3. So that is how we express a complex number in logarithm form. So log 1 plus I root 3. So take the complex number, find the modulus and argument, and then you have the log of the modulus plus I pi over 3, where pi over 3 is the argument. You observe that this log 2 is the real part, and this I pi over 3 is the imaginary part. So that is how we express complex number in logarithm form. So the next thing now is De Moivre's theorem. Very common and one of the most used aspects of this complex number, De Moivre's theorem. Suppose we have a complex number z. A complex number z that was expressed in polar form as r into bracket cos theta plus I sin theta. So De Moivre's theorem says that if I take the nth power of this complex number, z raised to power n is like having r, let me use a big bracket like this, r into cos theta plus I sin theta all raised to power n, right? So it will now equals to this power n will affect this r as this, r raised to power n. And this power n will affect this cos theta like this, cos n theta. So this power will just multiply the cos that is there, the angle that is there, plus I sin n theta. That's z raised to power n. And if I also take z raised to power minus n for example, so z raised to power minus n, that one will also be r raised power minus n into bracket cos minus n power that I'm taking. It will also multiply this one. I will have minus n theta like this plus I sine minus n theta. And because of properties of cos and sine that we discussed earlier, that cos is an even function. So z raised power minus n will be r raised power minus n. Cos minus n theta will still give us cos n theta. That minus will not have any effect. But sine minus n theta now, that minus will come to the back of this sign. So now turn this one to minus I sine n theta for all n. So this is De Moivre's theorem. So we are going to look at 3 applications of this De Moivre's theorem. Applications of De Moivre's theorem for all n. Application of De Moivre's theorem. Now, application 1. Application 1. Application 1. Now, the application 1 is about expansion of sine raised to power n theta and cos raised to power n theta. So how do I expand sine raised to power 5? Sine raised. Now, application of De Moivre's theorem. So application 1. Application 1. So application 1 is expansion of sine raised to power n theta and cos raised to power n theta. So how do we expand sine raised to power 5, sine raised to power 7, so and on like that. Now, suppose we are having a complex number z equals to r into bracket cos theta plus I sine theta. And then the inverse of this, z raised power minus 1, that's r raised power minus 1 into cos theta minus I sine theta. I believe we know how this one turns to minus, because if I put minus 1 here now, that minus 1 will affect this to see because cos is an even function. That minus 1 will affect this, so sine is an odd function. So that is how I got z raised power minus 1. Now, let's set the modulus of this complex number to be 1. So in both sides, let's set r to be 1. You know we are going to have z is equals to cos theta plus I sine theta, and then z raised power minus 1 is cos theta minus I sine theta. Now if I add these two equations together, if I add them together, you know we are going to have z plus z raised power minus 1. So let's say z raised power minus 1, that's 1 over z. So adding will cancel out these two, because this is plus I and minus I. They will cancel out, everything here will be 0. So these two will be left alone. So this one will be 2 cos theta. And if I subtract, we are going to have z minus 1 over z. Subtraction will do what? This one will cancel out. We are going to have this one. So it's equals to 2I sine theta. So z plus 1 over z is 2 cos theta. Z minus 1 over z is 2I sine theta. So we need these two equations. Now if I generalize, suppose I now take the square now. If I take square, z square. So from here now, z squared, according to De Moivre's theorem, this cos 2, these two will multiply this. It will turn to cos 2 theta. This sine theta, these two will multiply this, plus I sine 2 theta. And if I also take z minus 2 as well, z minus 2. So z minus 2, that minus 2 will multiply this. It will turn to cos 2 theta. To see the cos 2 theta, because if minus 2 multiply cos theta is an even function, we are having cos theta. Then Or if minus 2 multiply this sine theta according to the Movies theorem, so that minus will change this one to change this plus to minus. We're having minus I sine 2 theta. So if I do the same, if I add and subtract, z square plus 1 over z square, if I add these two, so adding will cancel out this. We are going to have this one. So z square plus 1 over z square is 2 cos 2 theta. And if I also subtract, z squared minus 1 over z square, subtraction will do what? Subtraction will cancel out this. We are going to have this 2. So is equals to 2i sine 2 theta. So with that now, we've generated a trend. Z plus 1 over z is 2 cos theta. Z minus 1 over z is 2i sine theta. Z square plus 1 over z square is 2 cos 2 theta. Z square minus 1 over z square is 2i sine 2 theta. So we can now generalize that Zn plus 1 over Zn is 2 cos n theta. And also Zn minus 1 over Zn is 2i sine n theta. So we also need these two formulas. Now let's now apply it. So let's now, for example, let's expand cos raised to power 4 of theta. Cos raised to power 4 of theta. So why are we even doing this? Why are we expanding cos raised to power 4? Because all the things that I've been talking about so far is x plus iy, real and imaginary part. Why are we using this? The reason why we are expanding all this big power of trig is that sometimes they can ask us to integrate, let's say integrate from 0 to 2 pi cos raised to power 7 x dx. Complex analysis. So if they ask us this thing in complex analysis now, so they are not expecting me to be using integration by parts in calculus or reduction formula or anyhow. So I would just say yes, I can actually expand cos raised to power 7 into smaller pieces of sine and cosine, and with that I can integrate one by one easily. So that is why we are expanding cos raised to power 4, because if they ask us to integrate a trig function, let's say sine raised to power anything, so and that power is very big, so we can go by expanding this cos and sine, and then we now integrate one by one. Now I want to expand cos x raised to power 4 of theta. Now if you can recall from here that where I started from, by saying z plus 1 over z is 2 cos theta. Here now I need cos raised to power 4. You know, if I start from here now, if I say starting with z plus 1 over z, what is z plus 1 over z? Z plus 1 over z is 2 cos theta, right? But what do I need? I need cos raised to power 4. So if I now take the fourth power of both sides, if I take the fourth power of this side and this side, I'm going to have z plus 1 over z all raised to power 4 like this is equals to 2 cos theta all raised to power 4 as well. So I will now expand what I have on the left hand side using my binomial expansion. If I want to expand z plus 1 over z raised to power 4, it's like z4 1 over z0, you can still remember, plus z3 1 over z1 plus z2 1 over z2 plus z 1 over z3 and plus 1 over z4 is equals to what? Is equals to this part is equals to 2 cos theta all raised to power 4. Okay. From here now, 1 over z raised to power 0, anything raised to power 0 is 1. So we are going to have z raised to power 4 plus 1 over z1 and z cubed. So this one will remain z squared. Z squared times 1 over z squared. The 2 will cancel out. We are going to have 1. Z and 1 over z raised to power 3. So this one will remove 1 from here. We are going to have 1 over z squared. And 1 over z4 will be there as 1 over z4 is equals to 2 cos theta all raised to power 4. And you remember that anytime I expanding using Pascal triangle, I'll put the coefficient. So if you know, you remember 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1 are the coefficient of power of 4. So if I put the coefficient, this is 1, 4, 6, 4, and 1. Okay? So 1, 4, 6, 4, and 1. 1, 4, 6, 4, and 1 are the coefficients. So from there, we are going to have, let me write it again. This is Z4 plus 4Z squared plus 6 plus 4 over Z squared plus 1 over Z raised to power 4 is equals to 2 cos theta all raised to power 4. Now, if I collect like term, collecting like term, this is Z4. This is the reciprocal of Z4, 1 over Z4. This is Z square. This is 4 over Z square. I can factorize them by saying 4 into Z square plus 1 over Z squared. And this is 6. I only have 6. Is equals to what? Is equals to 2 cos theta all raised to power 4. Z4 and 1 over Z4. Go back to this side. Zn plus 1 over Zn. Zn plus 1 over Zn is 2 cos n theta. Zn minus 1 over Zn is 2 I sin n theta. So Z4 plus 1 over Z4 will go by this. Zn plus 1 over Zn is 2 cos n theta. So Z4 plus 1 over Z4 is now equals to 2 cos 4 theta. Here now, our n is 4. Okay? Plus 4 into bracket Z square plus 1 over Z square. Zn plus 1 over Zn is 2 cos n theta. So Z square plus 1 over Z square is 2 cos 2 theta. 6 is 6, so nothing is equals to 2 raised to power 4, 16. Cos raised to power 4, cos raised to power 4 theta. So what do we have left now? Open the brackets. 2 cos 4 theta, 4 times 2, 8 cos 2 theta plus 6 is equals to 16 cos raised to power 4 theta. So divide both sides by 16. So that is cos raised to power 4 theta. So if I divide both sides by 16, cos raised to power 4 theta is equals to 2 divided by 16. That's 1 over 8 cos 4 theta. 8 divided by 16. That's 1 over 2 cos 2 theta. 6 divided by 16. That's 3 over 8. So this is how we will expand cos 4 theta using De Moivre's theorem, cos raised to power 4 theta. So I started with what? I started with Z plus 1 over Z equals to 2 cos theta. Why not Z minus 1 over Z? So assuming I want to expand sine raised to power 4 now, I will start with this part. I will start with Z minus 1 over Z is equals to 2I sin theta. Then I will take the fourth power of whatever power I'm going. Then I will expand binomial, and then you collect like term and do all the simple algebra. Now that is one application of De Moivre's theorem, expansion of cos raised to power n and sine raised to power n